Modern artificial intelligence relies on a mathematical engine called the chain rule. This rule provides a systematic way to calculate how a small change at the beginning of a long multi-step process affects the final result at the very end. In the context of AI, it is the fundamental tool that allows a computer to look at a mistake it made and trace that error back through many layers of processing to identify exactly which part needs adjustment. To visualize this, consider a relay race where 4 runners are carrying a baton. If the final finish time is too slow, which we can call the error, the coach needs to determine who is responsible. Was the 4th runner physically tired? Or was the 4th runner slow specifically because the 3rd runner's handoff was poorly executed? The chain rule acts like this observant coach looking at that final time and multiplying the slowness of every single handoff to determine how much the first runner's initial speed actually contributed to the total delay at the finish line. In mathematics, we often deal with nested functions, which are functions inside of other functions, similar to a set of Russian nesting dolls. If you have an initial variable x that changes a second variable y and that y in turn changes a final variable z, then x is indirectly causing a change in z. To find the total impact of x on z, you do not need to guess. You simply multiply the individual links of the chain together. The single takeaway to remember here is that by multiplying these local links, we can perfectly measure a global end-to-end effect across any system. Now that we see how the chain links multiply together visually, let's break down exactly how we calculate these specific links step by step. To visualize this chain rule process, we can break it down into 3 distinct steps. First, you calculate how much your middle variable, y, changes when the initial input x moves. This is your first derivative, represented mathematically as dy over dx. Second, you calculate how much your final output, z, changes when that middle step, y, moves. This gives us our second derivative, dz over dy. Finally, you multiply these 2 independent values together to find out your total impact. Let's look at the core formula for the chain rule right here in the center to see how this pieces together. The term on the left, dz over dx, is what we ultimately want to find. As outlined below, it represents the total change in the end result, z, based on the very first input, x. This is your final answer. Moving to the right side of the equal sign, the first term is dz over dy. What does that actually mean? It represents how much the end result, z, cares about or is sensitive to the middle step, y. Right next to it, we multiply by dy over dx, which represents how much that middle step, y, cares about the starting input, x. By multiplying these 2 step-by-step sensitivities together, we completely bridge the gap between the start and the finish. In summary, the total rate of change is simply the product of the rates of change at each individual step in the process. Another great way to intuitively grasp this compounding effect is by thinking of a chain of interlocking gears. So taking those step-by-step changes and multiplying them together. Another intuitive way to understand this is through a chain of gears in a watch. If you turn this small input gear, it physically forces the medium gear to turn, which then ultimately drives the large output gear, the hour hand. To figure out how fast that final hand moves when you turn the input, you simply calculate the product of all the individual gear ratios connected in between. We see this exact same cascading logic applied in real-world supply chains. Imagine the price of a barrel of fuel goes up. That is our input. It directly increases the costs for shipping.
And that shipping increase forces an upward change in the final output, the price of bread. Using the chain rule, we can write this out mathematically. The total change in the bread price relative to the fuel price is calculated by taking the change in bread price relative to shipping cost and multiplying it by the change in shipping cost relative to fuel price. This mathematical chain allows a company to track the flow of costs through the system and calculate exactly how a $1 increase in fuel costs will ultimately impact the final shelf price for consumers. A major cutting-edge application of this is in Google search ads. Google uses massive neural networks to predict whether or not you will actually click on a specific ad. These networks are composed of many distinct layers of neurons which function exactly like the interconnected gears in our watch. When the AI makes a wrong prediction, Google uses the chain rule to perform a process called backpropagation. The system travels backward from that wrong prediction, multiplying the changes across the layers to adjust millions of tiny internal weights. By understanding exactly how much each individual layer contributed to the overall error, the system updates itself to be more accurate the next time. Now that we see how essential this cascading logic is, let's look at how we can actually code these chain reactions using a tool called SymPy.
Just like we multiplied gear ratios to see how fast the final hour hand moves, we can do this exact same calculation mathematically using a Python library called SymPy. We start by importing SymPy. This library is special because it performs math using letters and symbols just like we do on paper, rather than just crunching numbers. First, we define our starting variable x. Next, we set up our functions. Think of these like Russian nesting dolls. This green doll represents our inner function. We define it as y equals x squared plus 5. You can see how x goes in and y comes out. Then, we define our outer nesting doll. This purple doll is our outer function, z equals y cubed. It takes the output from the first doll and transforms it again. Now, if we want to know how a change in our very first input x ultimately affects our final output z, we use the command sp.diff of z, x. This tells the computer to automatically apply the chain rule. It immediately spits out this final output formula. How did the computer do this behind the scenes? It followed the exact same rule we learned. It took the derivative of the outer function, which is 3y squared, and multiplied it by the derivative of the inner function, which is 2x. Finally, it substituted the original equation for y back in to get everything in terms of x. This clear flow from input to output is the chain rule at work. Let's test this intuition with a few quick questions at the bottom. First, if y changes twice as fast as x and z changes 3 times as fast as y, how much faster does z change compared to x? You just multiply the rates. 2 times 3 means z changes 6 times as fast. Second, why do we call it a chain? Look at this diagram of neural network layers. Every single layer directly depends on the calculations from the layer immediately before it. They form a literal, unbroken chain from the initial input to the final output. Third, think back to our relay race analogy. What happens if this third runner is completely perfect and makes 0 errors? Mathematically, if any single link in our chain has a rate of change or derivative of 0, the product of the entire chain becomes 0. This means the blame or the error signal stops right there and cannot flow backwards any further. Let's finish with one manual practice problem to lock this in. We are given an inner function u equals 5x plus 2 and an outer function y equals u squared. We want to find the total derivative dy over dx. Step 1. Find the derivative of the inner function u with respect to x. The derivative of 5x plus 2 is simply 5. Step 2. Find the derivative of the outer function y with respect to u. The derivative of u squared is 2u. Step 3. Multiply these two derivatives together. 5 times 2u gives us 10u. And step 4. Substitute our original expression for u back into the equation. So 10 times the quantity 5x plus 2 distributes to give us our final answer, 50x plus 20. This step-by-step multiplication of nested rates is the core of the chain rule, allowing us to easily solve complex multi-layered dependencies.